thank you very much for the introduction and for inviting me to speak. I was trying to think back to the first time when I crossed paths with Michel, and I think it was actually when I was still a student. So I just learned about complex Hodge theory, and there was this spring school in Rennes about classical and p-adic Hodge theory. And I'd never been to a conference before, but it looked kind of interesting. So I applied, and I was able to go there, and it was actually one of the nicest conferences that I've been, like even now, looking back, and it was the first time I saw p-adic Hodge theory. It got me really interested in it, and I'm still thinking about it now. Yeah, so thank you very much for that initial impetus, and for the conversations we had after, and happy retirement. Okay, so my talk today is not precisely about p-adic Hodge theory, but still about non-Archimedean geometry. It's about a relative Poincaré duality in non-Archimedean geometry, and the goal will be to prove some Poincaré duality statements for non-Archimedean spaces. So all of what I'm going to say today is going to be in joint work with Shizhang Li and Bogdan Zavyalov. Okay, before I talk about non-Archimedean geometry, let me maybe recall the story that we have in algebraic geometry. So I'm not going to state the most general theorem one can state, but one thing that is proven in SGA4 is that if we start with a smooth proper morphism of schemes, and we take some integer that is invertible on the base, and some z mod n local system, then there's two types of statements that one can make about the push forward of this local system along this smooth and proper morphism.
Thanks.
Yes, thank you. And I guess I should also say étal. So the first one is a sort of finiteness theorem. Says that the higher direct images of the local system along the morphisms are again local systems. And this essentially follows from a smooth and proper base change. And then the second statement that one can make is that these high direct images satisfy Poincaré duality. So in this generality, it is more convenient to work with the derived push forwards. So if f is of equidimension d, there exists a trace morphism from the push forward of z mod n, appropriately Tate twisted and shifted back down to z mod n on the target. And this induces us a pairing. From the push forward of L, tensor the push forward of the dual. So first, via the cup product, this maps to the push forward of the tensor product of the two. And then one can evaluate. So this sends us to the push forward of the twist and shift of Z mod n. And now we have the trace morphism that sends this to Z mod n. And the statement is that this pairing is perfect. So that is, there's an adjunction morphism from here to the R home, and this map is an equivalence.
So of course it is just a statement on cohomology shifts, because for Z mod n there is no higher x for. So it's only a cohomology shift.
Yes, yes. So yeah, one can use that as Z mod n is an injective module over Z mod n. Yeah. Okay. So now let me maybe move on to non-Archimedean geometry. So there will be some representation theory this afternoon, so I'm assuming that not everyone is familiar with these non-Archimedean spaces. I certainly can't introduce them in detail here, because it would take an entire lecture course, but let me maybe still give a very small idea of what they look like, since we'll also be using some of this later in the talk. So very roughly, these non-Archimedean spaces that I want to talk about will be rigid-analytic spaces over some C, which should be some algebraically closed non-Archimedean extension of, say, QP. So for example, you could take the completion of the algebraic closure of QP. And they're supposed to be somewhat analogous to algebraic varieties over C. So what does this mean? Somehow the local model here is affine space, and then the local model here is something like a closed unit disk. So and so when you have a space like this, you would want to know what the functions on it are. Or, well, first of all, what are the points on it? So the points should just be those d-tuples in C to the D. This is the mic, okay?
Looks okay.
Whose values are bounded by 1. So in other words, OC to the D. And then there's also functions on this, which should just be those power series that actually converge on this set over here. Okay, and so then in general, a rigid space, locally it will look like the zero set of some of these functions.
TD.
Yeah, thank you. Okay. So in my talk, I actually want to think about rigid-analytic spaces in a slightly different way. So for algebraic varieties, it's often very useful to think of them inside of schemes. And in the same way, there is a fully faithful embedding of these rigid-analytic spaces, at least for quasi-separated ones, into the category of adic spaces. And again, I don't really have time to introduce what they are, but I just want to give you one example because it will be quite relevant later on. And that's that of the unit disk. So the idea is that the points of these more general spaces should correspond to valuations on the function spaces of these rigid analytic spaces. And so the example of the unit disk, these would be continuous valuations from a convergent power series in one variable to some totally ordered Devian group. Subject to some conditions. So there's the usual conditions that one requires of a non-Archimedean valuation. But then also we would like this sort of condition here, that these that the functions are actually bounded on this unit disk. So what this would mean concretely is that the valuation on OCT is supposed to be bounded by 1. Okay, and now let me just draw a picture or give some examples of such valuations. So if you think of this as the unit disk, then these points from before, they still give us valuations. So if we have some element of OC, the corresponding valuation would just take a function f. It would evaluate it at that point and take the absolute value in this non-Archimedean field C. Okay, so these are the points here, but there's more general points. So just like in schemes, we have points for irreducible subvarieties. Here, for some closed unit disks, we also have some points. You can do this for every unit disk, and then maybe there'll be some branches like so. So let me just give one example of those. So if we fix some radius, then the valuation that would correspond to the smaller disk around 0 of radius r, it sends f to the maximum over all points of this unit of this disk of radius r. And this will again be some real number. Concretely, if you write this as a restricted power series, this will be just sent to the maximum of the values of the coefficients times r to the I. Okay, and so lastly, I want to talk about one more point that's very special to these adic spaces and doesn't come up in other flavors of non-Archimedean geometry. So if you zoomed in here very closely, we'd see that there's actually a bit more points that point into the directions of these points in the unit disk. And so I was very careful here to not say that this group should have rank 1. So instead of just taking r here, we could also take some valuation that's valued in r times some other element. I'll denote it by 1 minus, and you'll see in a second why. So let me again just give one example of these. If we, can I actually call this r minus? So if we fix again some radius, we kind of want to take the same valuation as here, but now we want to say that the radius should be slightly larger, infinitesimally larger than this r. So to make this precise, we're kind of demanding here that the ordering is the lexicographical ordering, such that for all radii less than r, the r prime is less than the r minus is less than r. Okay, and then we can get again a valuation that sends this f to the maximum of AI times r minus to the I. So this will allow in here. Okay, this was some sort of very short introduction to adic spaces. Are there any questions at this point? Okay, I hope it is because everything is clear. So now I can state the first theorem. And let me give the attributions later and first tell you what the statement is. So it's quite similar to the statement that we have over here. If we start with a smooth proper morphism, okay, so now I have to replace these schemes by something else. And the best generality that we can hope for is a locally Noetherian analytic adic spaces. So if you don't feel comfortable with these, you can also just assume that they're rigid analytic spaces over C.
Sorry, what's the difference between analytic adic space and adic space again?
So here it's locally attached. So there's a
really locally.
Like, yeah, like half a knot. There's an half knot covering by
quotient of the Tate algebra. There's a covering by quotients of the Tate spaz of quotients of the Tate algebra. Is that what you said?
No, I just mean that there's a pseudo-uniformizer.
There's a pseudo.
yes.
So some topologically nilpotent element that's a unit in the ring.
And for locally Noetherian, do you assume that there is, integer ring is Noetherian, or what is locally Noetherian here? Because
yeah, so
it's kind of subtle for adic spaces.
right. So it means that locally it's strongly Noetherian.
Okay.
Yeah, but so we never really used this Noetherian hypothesis in a serious way. It's just that the formalism of Vital cohomology was only set up for these locally Noetherian spaces by Huber. So we have to make this assumption. Yeah. Okay, and so again, we fix an integer. That's invertible on the base, but so very importantly, there's two different characteristics now. There's the characteristic of the field, and there's the characteristic of the residue field. So here it would be 0 and p. And we only assume that it's that this n is invertible on the field, but not necessarily on the residue field. Okay, and now for these rigid spaces or these adic spaces, there's again a formalism of Vital cohomology, and we can take an Vital Z mod n local system. For the source, and then we basically have the same statements. So the high direct images will again be Vital Z mod n local systems for all I. And there's again a duality. Maybe I didn't have to assume this here. Let me assume it here. So again, we have a trace of the same form. Which again induces a pairing. It's the same pairing as here, so let me not write it out again. And the statement is that this pairing is again a perfect pairing in the same sense as over there. Okay, are there any questions about this statement? Okay, so then I should maybe give attributions. Yeah, maybe the first case that was treated was the one where this n is actually co-prime to the residue characteristics as well. And that was done by Berkovich, and later in the language of adic spaces by Huber. And so after this, people were kind of stuck for a long time. It wasn't really clear what. The statement can't really work if n is not invertible for the base. But the natural question is what happens when this n is invertible for y, but not on the residue characteristics. And the first general statement that I know of in this direction was by Scholze, who basically proved 1 for Z mod P local systems in the absolute case. And the methods are quite different from what Berkovich and Huber did. He used a lot of these perfectoid spaces that he introduced, or that he had introduced a year earlier. And then the relative case was proven in the Berkeley lectures with Jared Weinstein. And so then the natural question is if one can also prove an analog of 2. And in fact, this turns out to be true. So I think the first proof was announced actually in this very room by Geber, I think maybe in 2016. And then later, these methods were worked out in more detail by my co-author, Zavyalov, and there was a quite different approach by Lucas Mann. So all of these methods somehow use perfected methods in quite a crucial way, and they really only work for n equals p because of this. So here the idea is somehow to study formal models and reduce to some statement about formal models. And here the idea is to construct a six-functor formalism, but not for these Z mod n état local systems, but rather for O plus mod p sheaves. Okay, and so in our work we're giving a new proof of this theorem that's quite different. So maybe the first remark I should make is that there's almost no input from perfected methods. So there's exactly one place where we need them, and I'll point it out later. And maybe the second remark to make is that our proof works uniformly for all n. Okay, get some more remarks. So we have the statement for Z mod n local systems. One could also wonder what happens for QP local systems. And in fact, there's also statements one can make. So maybe the first version for QP local systems that I know of was proven by Lan Liu Zhu in a somewhat restricted setting. So I think they have to assume that this QP local system has a ZP lattice, and they work over a discretely valued field. But recently also a much more general version has been announced by Anschütz, Lepras, and Mann. So they essentially they generalize this approach of Mann using six-functor formalisms, and then also independently by Colmez, Gilles, and Niziol. And they're even able to get some stronger statements for partially proper morphisms.
So in the absolute case, the QP version kind of followed from the FP version in Zavyalov's paper?
If you have well, it depends on the coefficients that you take. So the problem is that, so if you just take QP coefficients, then yes. But the problem is there could be a QP local system that doesn't have a ZP lattice. And so then it's not.
So but the cohomology, it's known, although it was a mistake in Kedline stated some time ago, that the cohomology doesn't have to be finite dimensional. You have to use more general. For QP local system, you have to use much more sophisticated thing related to Banach-Cohen space. I mean, it's not really this as simple as you say.
Yeah, thank you. So yeah, I was a little bit careful by just writing there exist QP versions without saying what these versions are, but yes, so we don't really have an analog of one, but rather the statement should be that we get Banach-Cohen spaces, and also thank you for mentioning this paper of Kedlaya Liu, so they proved a statement, and they promised an update where some of the mistakes in this paper will be corrected. Okay, and so then the last thing that I want to mention is that there actually also exists a version for proper morphisms, so not necessarily smooth. Of rigid spaces and Zariski constructible sheaves. So I'm hoping I'll be able to say something about this later today. So this was also proven by us. And well, we think that there's a good chance that it also follows from Bogdan did with his six-functor formalism, but as far as I know, this has not been worked out. How do I reach the...
should be here.
Thanks. Thank you. Okay, I want to say something about how we prove these things, but before I do, are there any questions about the statements? Okay, then let me move on to some of the proofs. So the first thing that I want to tell you about is how we construct this trace map that I mentioned over there. So in the partially proper case, a trace map had been constructed by Berkovich. But actually, we're able to show that such a trace map exists, not just in the smooth proper case, but without imposing this properness assumption. And so somehow to prove this theorem over here, it's enough to have this trace map for partially proper morphisms, but for this more general version, it's really important to have a version that just works for all smooth morphisms. And also our construction is quite different from the one in Berkovich. And it really uses this geometry of adic spaces that I was trying to explain over there. So the statement is the following. It says there exists a unique way to attach to any smooth. Okay, we also have to have some technical assumptions. So to any such smooth morphism, a trace map now, if we don't have properness, we need to work with proper push forwards. Subject to some natural compatibilities. Let me just very briefly comment on this thought. So this is just some very technical condition that Huber needs in order to define this RF lower shriek. And it's somewhat related to quasi-paracompactness. So if your space is quasi-paracompact, then it is taut. Okay, so the first compatibility is that this trace is supposed to be compatible with compositions. Then we also want it to be compatible with pullbacks. And the next thing is that if this f happens to be a tau, there's actually another trace map that we could have written down. So this trace now it goes from here to here in the Ital case, and there's an adjunction of f lower shriek with f upper star in this setup, and the claim or the compatibility that we want is that this is just the co-unit for this adjunction. And then lastly, there needs to be some normalization. And for this, we're just comparing with the algebraic trace. So we want that for the structure morphism of P1 defined over an algebraically closed non-Archimedean field. So we could look at this trace map over here, but we could also look at the algebraically defined trace map and then take the analytification. And the required compatibility is that, that these two agree. Okay, yeah, so in fact, once we have this, then it will also be compatible with all algebraic trace maps. And yeah, let me say a little bit about how to construct such a map. So first of all, let me maybe say something about the uniqueness. So let's assume we have constructed such a map. Can we pin it down uniquely? And for this is a somewhat classical strategy. One can use the factorization of smooth morphisms, at least locally, as Ital morphisms. Followed by projections. Okay, so if this a trace map is to satisfy all these compatibilities, then okay, so then number 3 somehow, by number 3 it suffices to define it on here. And then number 3 also tells us what this trace map is supposed to be. And number 4 tells us what this trace map is supposed to be, because we can embed this into P1. Yeah, and then I guess we can take successive projections. And then the compatibility with compositions and pullbacks tells us that this trace map is completely determined by what we have here.
So implicitly you're using some cohomological dimension to know that you're really interested in the top direct image, and it's okay.
Yes, yes, certainly. In order to be able to glue these local trace maps, we need this statement here. Okay, and so in fact, this also kind of gives us a strategy how to define this trace map, right? Because we know that we can locally factor like this, and then we just take the Ital trace followed by the trace for P1. But of course, the problem now is that we just made some random choice here by choosing some factorizations, and it's not clear at all that what we defined does not depend on this choice. So that's what we have to prove in the existence. And so in fact, if you think about this a little bit, then you realize that it suffices to construct such a trace map or to show this independence of this factorization just for aphanoid curves. And some strategy like this was already done in the algebraic case in SGA4. So really, it suffices to think about what happens when x is an aphanoid algebraic curve. Is an aphanoid curve defined over some non-Archimedean algebraically closed field. Okay, and so in this case, we really need to use the structure of adic spaces that I was alluding to before. So we have to use that unlike for schemes, these adic spaces actually have a universal compactification. Okay, I guess that's true. But I guess these aphanoid curves, maybe it's not clear a priori that they have universal compactification because there are some opens inside of these algebraic curves. Okay, so we want to use this to define the trace. And I can't really explain to you what this is in general, but let me just explain it for you in this case of this unit disk. Seems like I messed up. Okay, good enough. Right, so we're in this situation over here, and it turns out this unit disk, as I described it for you, is not compact. And the reason actually comes from one of these higher rank points. So we could also zoom in over here. And it turns out there's another small point here that we can add. And let me just write down the valuation for you. So here I said we want to fix some radius that's infinitesimally smaller than r. But we could have done the same with bigger. So we could have looked at somehow this group over here, where now this r plus is just a bit bigger than r, but smaller than all the r primes that are bigger than r. And we can write down the same formula. Sorry, I hope this is legible. Sorry, come again?
For r less than 1 strictly, unless you want it to be contained in unit disk. But
yeah, so that's exactly the point. Yes, so right, thank you. Yeah, so as you pointed out, when r is equal to 1, then v of 0, 1 plus of t is just a bit bigger than 1. So this point v0, 1 plus is not in the unit disk. But it is in, so the universal compactification is at this point over here together with the unit disk. Are there any questions about this compactification? Maybe while I erase the board. Okay, let me leave this. Okay, and so now we utilize this to construct our trace map. And to do this, we need to look at an excision sequence. Actually, maybe it's better to do this on a big board. Yeah. Okay, so we want to use excision for the composition of the compactified unit disk into the unit disk and this additional point. So if you know about adic spaces, you know that there's a small catch here and that this is not really an honest adic space anymore, but I assume if you know this, then you also know how to fix it. So let me not talk about it. The relevant part of the excision sequence is the following. So now I have to take a Z mod n1, so the nth roots of unity. This maps to the cohomology of this additional point. And then this will map to the compactly supported H2 of the open unit disk. Okay, and so the next term will be the second cohomology of this, this compact disk. But actually it turns out that, that by an Artin-Grothendieck vanishing result, this is actually equal to 0. Okay, and so the trace map is supposed to be a map from here to Z mod n, and to define it, we'll define a map from here to Z mod n, and then see that it's 0 on this term over here. Okay, so let's start computing these things. So here, this can just be computed by Kummer theory. The ring of functions on this disk is still CT. And so if we want to take the first UN cohomology, we just get this quotient.
And you have to know that the Picard is 0.
Yes, thank you. Yeah, so here we're also using, so the Kummer sequence, there's some H1 of GM term, but we're using that this is 0, which just boils down to the fact that this is a UFD. Okay, but so now one can check that the restricted power series here is a unit if and only if the 0th term is the biggest one. So this is also the same as C cross times 1 plus MCT T. Okay, and then I have to take the quotient by this mod n. Okay, and okay, now this field here was algebraically closed, so this group here is actually divisible. And so this is just the same as 1 plus MCT T mod n. Okay. Now what about this term over here? So again, there's a result of Huber that tells us that this is just the algebraic étale cohomology of the residue field at that point. Suitably Henselized. And then one can again use Kummer theory to compute this. Okay. And so it turns out that this valuation, so this V 0, 1 plus, it was a valuation on these rings of functions on the unit disk, but it actually extends to a valuation on this field over here. So the valuation, the value group here was r greater than 0 times z, basically. Okay. And now, of course, this map doesn't descend to here, but if you mod out by n, here it does. Okay, but again, this group is divisible, so this quotient is just z mod n. Okay, so let me go through it again. So we start here, which we identify with this quotient over here, and then I constructed for you, just from the valuation, this rank 2 valuation, a natural map to z mod n. And now the only thing left to do is to see that it's 0 for this term over here. But that's also quite easy, because if you take a function in here, so this is of the form 1 plus some I equator equal to of ai t to the I, where these ai are on the maximal ideal. So the valuation should take the maximal value. But since all of these are in MC, the maximal value of these coefficients times r plus is just this one. And this maps to 0 here. So we get a natural map from this compactly supported cohomology to z mod n. Okay, and then in the general case, one has to do similar work, but it gets a lot more complicated because we have this curve here, and then one has to check that at all these additional points that one adds in the universal compactification, this composition is still 0. Okay. Are there any questions about this argument? Yeah, so in this general case, one has to use some sort of residue. So the way that one would do it is to say that these have a natural interpretation as mu n torsors. And so these line bundles on the generic fiber, they can be extended across most of the special fiber of a formal model as well. And so then really what this map here is, it's the residue at the additional points that correspond to some points in the special fiber and cannot be seen in the generic fiber. And then the fact that that this map is 0 is just the fact that the degree of a principal divisor is 0.
Is there some way to think about this analytically as some integration along the adic boundary, like a Cauchy formula?
Yeah, we were wondering about this. It seems very natural, but we can't make it precise. Yeah.
So what did you write in the last line here?
Here? I wrote 1 times 1 plus to the 0. But so I just mean an element in this group over here. So the absolute value of the largest coefficient is 1. And this is t to the 0. That's where it comes from.
So these extra points will always be ranked 2 in the universal compactification? They will
Sorry.
always be ranked 2, these extra points in universal compactification? Or
Yeah, yeah. So that's something that you have to prove in this case of curves, but it will be finitely many rank 2 points. Yeah. Okay, so this is the construction of the trace map, and since the last talk was about prismatic F crystals, and since that's also something that Michel has worked on, let me maybe point out that one can't just use this trace map in this situation over here, but also to prove similar statements for prismatic F crystals. So we can use this trace to define a trace map for prismatic F crystals. and prove a version of Poincaré duality. So this was done in joint work of myself with Haoyang Guo. Although, if I'm being honest, so we did this in the proper case, so one could have also used the Berkovich trace. And that's also what we did.
You said that you did it in.
Yeah, so the setup is the following: that we have a smooth formal p-adic scheme defined over a ring of p-adic integers. Yes, yes. So we have to prove that there's a functor from these crystals to a tau local system on the generic fiber, and that this functor is fully faithful.
So this compactness is a genuine analytic adic space, or it's so there's a d bar here.
Yeah, so you can't see it in the Berkovich theory, if that's the question. Or like in the Tate-Switcher theory.
Okay, so it's an adic space.
The d bar is an adic space, but just this point is not.
Okay.
Okay, maybe another remark that I should make is that this calculation over here, it also shows that there can't be any, at least naive form of Poincaré duality for these non-proper spaces. So in algebraic geometry, one can also make some statements if the morphism is just smooth. But here it's kind of difficult. So let me maybe just summarize this. So let's just work over C of mixed characteristic 0, p and take FP coefficients. So then what a computation like this shows us is that this is FP in degree 0. It's okay, what we saw over there. Degree 1 and 0 here. And similarly, one can compute that the compactly supported cohomology is 0 outside of degree 2. And in degree 2, it is equal to, well, the co-kernel that I wrote down over here. And so you can see that, I mean, this group is huge. It even depends on what the cardinality of the residue field is. Here it's 0. But on the other hand, this group over here is huge, but this group is just FP. So at least if you try to formulate things naively, you won't be able to get any sort of Poincaré duality. Okay, so now I want to also say a little bit about the idea of this new proof of theorem A. And so somehow the idea is that the statement here is completely diagrammatic. It can just be like it checks. It boils down to checking the commutativity of some diagrams once one has defined this trace map and cycle class maps. So for this, we need to use that perfect complexes in the derived category are the same as dualizable objects. So dualizable, recall, this just means there exists a dual object together with evaluation and co-evaluation maps. That satisfy some natural compatibilities. Let me maybe write down one of them. So we could start with E and then take co-evaluation times identity to go to E tensor E dual tensor E. And then we could apply identity times evaluation to go back to E, and we want that this is the identity morphism. And there's another one that looks exactly the same. Okay, so, and also it turns out that in this case, this E dual is just given as the R hom from E to Z mod n. Okay, now the idea is the following. We start with some dualizable complex on X, or we start with some perfect complex on X is the same as dualizable. If we can show that the push forward of it is again dualizable, then it will again be perfect. So this will give us some finiteness statement. And if we also know what the dual is, this will give us the second statement about the duality. So goal is to show that for any dualizable complex E, the higher direct image is again dualizable. And the dual is exactly given by this other complex over here. Okay, and let me maybe just say, so dualizable, it means that there's these evaluation and co-evaluation maps. So let me just tell you what they are. And the evaluation map I basically told you already. So we want a map from here to a Z mod n. But for this, we can just take the cup product and then take the evaluation for just these complexes. And finally, I use the trace. The co-evaluation is maybe a bit more tricky. So we want a map that goes from Z mod n to E tensor the push forward of E dual D shifted by 2D. Okay, so the first thing that we want to use is that, okay, let me maybe start here. So there's some things that you can just do if you follow your nose. So this maps to R of lower star of Z mod n. And then maybe the next thing that you would do if you followed your nodes would be to say, okay, this maps to here. Okay, and now it's maybe not completely clear what to do, but you can use the following diagram. So the product of x with x over y it admits a diagonal embedding from x, and these compositions here are the identity. And so one thing that one can show is one always has a Kuhneth map from here from here to RH lower star of E tensor E dual, twisted and shifted. And so it turns out that in this situation, this Kuhneth map will be an isomorphism. Yes, thank you. And so this is exactly where we need these perfected methods. I said before that there's one input. Yeah, exactly. Right. Yeah, so I think the first place where it's written down is in the paper of Butt and Hansen, but it basically follows from the primitive comparison theorem and from the theory developed in Huber's book. Okay, so we want to get somehow here. And for this, we can use the projection formula. So this is the same as our... yeah, thank you. Thank you. Yes, I was getting ahead of myself. Right. Right. So this is by the projection formula the same as RH lower star of E box tensor E dual tensor delta lower star of Z mod n, and now we can apply a cycle class map. For the diagonal, so this map will send this to a Z mod n twisted by the codimension of the diagonal, which is exactly D, and we will land here. And so then there's a gigantic diagram that one has to check commutes to get this sort of statement. And it takes quite a bit of work, but somehow the essential input is that the trace of a cycle class is equal to 1. Okay. I'm already out of time, so let me stop here.
Questions or comments?
So I have a question. So your proof for prismatic F crystals, so it's not a direct proof. You use your result in that case.
So what we need to use is that there exists a trace map for smooth improper morphisms, and you could either take Berkovich's or ours. Yeah. But once you have this, so once you have constructed a pairing, then.
But you need your statement.
No, we don't need the point. No, and so in fact, this would also give a new proof for crystalline local systems, but it would be a very complicated proof. But yeah, the idea is to just reduce mod the prismatic ideal I, and then check some duality for Hodge-Tate crystals, which basically boils down to Grothendieck duality.
Question? Question here?
About removing the smoothness hypothesis?
Right, yeah, so for this one, let's write it here. One needs to work with this formalism of Zariski constructible sheaves. So if you have any rigid space X over a non-Archimedean field K, you can look at the category of Zariski constructible sheaves. And Butt and Hansen proved that there is a notion of dualizing complex in the setup. And so this dualizing complex, it will give you a Verdier duality functor from on here, given by R Homs into omega x. Okay. And so then the statement is that push forward along a proper map commutes with Verdier duality. Yes, case of characteristic 0.
Otherwise, the pathological, the risky constructible that you have to.
Yes,
that's not. And also, even if you fix it, you have to need some other methods probably to.
Yes,
so it's not so.
Right, just to even prove that push forward preserves the risky constructible sheaves already uses this hypothesis. Right, and yeah, the idea, just very briefly, to construct the trace map in this case is to just say if we have a map from X to Y, it factors through the graph morphism. And so, like at least if this Y is separated, then we get a closed immersion here where we know how to define the trace map, and then here, this map is smooth but not smooth and proper. So here we can use this trace map that we defined.
Yeah, X is smooth.
Yes, X is.
No, but you can also, but one can also reduce to this. I mean.
Yeah. So there's an additional reduction to the case where X is smooth by using resolutions of singularities.
Which is available only in characteristic 0 for the moment.
Yes.
More questions? So I had just a very simple minor question. Vague remembrance that dualizable was related to ULA.
Uh-huh.
Can you remind me of this case?
Okay, so maybe I also need to think about the precise formulation of this. But yeah, sorry, let me maybe not say it now.
Universally locally acyclic or locally acyclic by so it's related to dualizable, I think.
Voted for schemes or rigid?
No, in the classical case.
Classical means schemes.
Yes. The last part of your talk. I think it was in a paper by John Richard. Yeah?
Yes.
But I just forgot. It's so I thought. But it doesn't appear anymore.
It does not appear now.
It doesn't appear. You don't use any relation suffix.
No. We don't.
What is the paper you mentioned?
Yes.
But this is just dualizable with respect to the tensor product on complexes. In that work, it's you have this 2 category, and you're asking, a sheaf is viewed as a morphism, and you're asking it to have an adjoint or something. So.
But
it's totally different.
Some precise relation between the two notions, and between dualizable and
no relation. I mean, it's totally different.
No, there exists for schemes. There are equivalent.
No, it's totally different.
Yeah, as he said, they have to consider different tensor product, not and different 2 categories.
Yes, but there is.
Yeah. Then it's
but different context. So no more questions, and we thank the speaker again.